Welcome back, friends. Yesterday, I've given this numerical to solve. Hope you have done with this one. A substitution kind of question. 120.22 picofarad per meter. Very good, beta. See here. A coaxial cable capacitor of inner radius, how much? 1 mm. And outer radius 2 mm. Has a capacitance per unit length of 172 picofarad per meter. If the ratio of outer radius to the inner radius is doubled, the capacitance per unit length is. Yes, beta. So what is the capacitance formula for this coaxial cable? Capacitance is equal to C is equal to 2 pi epsilon L by natural log of B by A. Is asking capacitors per unit length beta. So what you can do? You can bring that L here. C by L is equal to 2 pi epsilon divided by natural log of B by A. What is B value beta? It is 5 mm. 5 milli by 1 milli, which is equal to how much? 172 pico, means 10 to the power of minus 12. So which is 2 pi epsilon is equal to natural log of 5 into 172 into 10 to the power of minus 12. So what actually it is? Now I'll call this as a C dash beta. Now we want a C double dash. If the outer radius to the inner radius is doubled, keep this one aside. If the outer radius to the inner radius is doubled, means what? A by B. A by B ratio is equal to 2 into 5. Outer radius to the inner radius ratio is 5. It is 2 into 5, which is 10. Clear? Then what is its new capacitance per unit length, which is equal to 2 pi epsilon divided by natural log of, outer radius to the inner radius beta. Here it is B by A. Double dash. B by A double dash, which is equal to 172 into 10 to the power of minus 12 by into natural log of 5 divided by natural log of 10. So here it is, you can check out 120.22 into 10 to the power of minus 12 or 120.22 picofarad per meter. See, unless and until it is mentioned, you cannot take this epsilon is equal to epsilon naught. Why? Because the capacitor can be air filled. It could be a dielectric field also, isn't it? Fine. So that is the thing. Now let us have one more question, beta. I'll going to turn the page here. The capacitance of the arrangement shown in figure is dash picofarads. Here it is epsilon 1, here it is epsilon 2, here it is epsilon 3. The distance from here to here it is 10 centimeters. Here to here it is 10 centimeters. Here to here it is 20 centimeters. Here to here it is 10 meters square. These are the plates. And he has also given epsilon R1 is equal to 1. Epsilon R2 is equal to epsilon R1 is equal to 1. Epsilon R2 is equal to 2. Epsilon R3 is equal to 4. So it is a composite parallel plate capacitor beta. Then you need to develop its equivalent model. How can you develop? This is a plate here, one more plate here. So this one and this one are series. And this one, the resultant is parallel with this one. Yes, that is the thing. So what you can do, let us use some terminals here. Here it is A. Here it is B. How this equivalent model can be written? Like this. C1 is in series with C2 beta. And the resultant will be in parallel with C3. Here it is C1, here it is C2, here it is C3, here it is A, here it is B. So these type of models are also noticed. Just I wanted to show. Hope you can proceed with this one, right? I'm going to turn the page here. What is C1 beta? C1 is equal to epsilon 1 into A1 by D1 beta, which is epsilon naught, epsilon R1 is 1 area. How much is the area? This one. It is 10 centimeters square. So 10 into 10 to the power of minus 4. Divided by spacing. What is the spacing from here to here? 10 centimeters. 10 into 10 to the power of minus 2. Then C2. C1 is equal to C2, right? Not C2. C1 is not equal to C2. Here is epsilon R2 is there. So here it is epsilon 2 into A2 divided by D2, which is equal to epsilon naught into epsilon R2 is 2 beta into 10 into 10 to the power of minus 4 divided by spacing is 10 into 10 to the power of minus 2. C3 beta then. Epsilon 3 into A3 by D3 beta. And one more thing here, these two are in series. So what is the resultant? C1 into C2 by C1 plus T2. The resultant is in parallel with this one. So what is the capacitance between this one? Hope you would have learned from your signal, this circuit theory. What is the capacitance between A and B? C1, C2 divided by C1 plus C2 plus C3. That is all the thing. Yeah. So there C3 is epsilon 3 is epsilon naught into 4 into area. What is area beta? Rest our area is 10 centimeters square. 10 into 10 to the power of minus 4. What is the spacing here beta? Here to here spacing is 10 centimeter. Sorry, 20 centimeter. 20 into 10 to the power of minus 2. So here it is epsilon naught into 10 to the power of minus 4. Here it is 2 into epsilon naught into 10 to the power of minus 4. Here it is 2 into epsilon naught into 10 to the power of minus 4. Is that correct? Minus 2 beta. So C1 into C2 beta. Now give me the answer here. Now you can easily do. What is this C1 in parallel with C2? C1 into C2. This value CAB is equal to epsilon naught into 10 to the power of minus 2 into 2 into epsilon naught into 10 to the power of minus 2 divided by 3 into epsilon naught into 10 to the power of minus 2 plus 2 into epsilon naught into 10 to the power of minus 2. So what is this CAB beta? This is 8 by 3 into epsilon naught into 10 to the power of minus 2. Am I correct? Substitute value beta. 8 by 3 into 1 by 36 pi into 10 to the power of 9 into 10 to the power of minus 2. So evaluate its value. It is 0.23 into 10 to the power of minus 12 farad or 0.23 picofarad. Clear beta? Let us have one more question. Yes, very good, very good. I'll going to turn the page here. Let us have one more question beta. excuse, an hollow metallic sphere of radius r is kept at potential of 1 volt. The total electric flux coming out of the concentric spherical surface of radius r, which is greater than small r, is. Options are given: 4 pi epsilon naught r, option B 4 pi epsilon naught into capital R, option C 4 pi epsilon naught r square, option D 4 pi epsilon naught r square. Yes, what is the answer? This was one of your gate question, asked for 2 marks. Very good. Yogesh Gaikwad. Abhigit. Here, today's session will be only up to 8 p.m. There will be a power cut from 8 p.m. onwards. So the today's session only is up to 8 p.m. Fine. Here is the thing, beta. Let us try to understand the question properly. An hollow metallic sphere of radius r is kept at a potential of 1 volt, beta. The total electric flux coming out of concentric spherical surface of radius r, which is greater than small r, is. Observe here carefully. There is a sphere, beta. Okay. Whose radius is there. Here is a sphere. Whose radius is r. And it is connected to the potential of 1 volt. And what is the charge induced on this one? I'll call it as a Q induced. So what is it? Is isolated sphere, beta. When it is raised to the 1 potential, there will be a charge induced on that. So isolated capacitor, capacitance value is C is equal to, by definition, capacitance is charge induced by voltage V. So which is equal to Q by 4 pi epsilon naught into A beta. So here the potential is 1 beta. Q induced is equal to 4 pi epsilon naught into R into 1 beta. So here it is. Charge induced is 4 pi epsilon naught into r beta. This is a charge induced on the sphere. Now, what actually the question is? Now, this the question here is the total flux coming out of the concentric spherical surface of radius r. Now, this charge, this sphere of radius small r is enclosed with the one more sphere. Yes. Here is the thing. What is the charge on this one? Here, charge induced on this Q. Now, this is enclosed with the one more sphere. He is asking what is the flux coming from this one, whose radius is greater than small r beta. From the Gauss law, what we know? The flux coming out of from any closed surface is equal to charge inside that. So the charge inside this one is charge on this one. Yes. So here, what we know from the Gauss law is the net electric flux is equal to charge enclosed beta, charge ENC. Charge enclosed is nothing but charge induced on the sphere, which is equal to, how much is that? 4 pi epsilon naught into R is a coulombs. Is the answer. Option A is the answer. Clear, beta? So here you should know the formula. Along with that, you should know the concept. Two concepts are involved. One formula, other one is a Gauss law. 2 marks question. Let us have one more question. The ratio of charges induced on two metallic spheres raised to the same potential is 6. The ratio of the surface areas of the area of the ratio of surface area of the spheres is. Options are given 6. Option B 1/6. Option C 36. Option B D 1/√6. Yes, beta. What is the answer? Very good, 36. Okay, see here. Let us have some rough diagram here. Here is there are two spheres, beta. The ratio of charges induced on the two metal spheres raised to the same potential. Potential is same. Is Charges ratio is 6. Is asking the ratio of surface areas here, right? Let us have some rough diagram here. Here is a sphere. It is having a radius R1. And the charge on this one is Q1. This is raised to the potential V1. There is a one more sphere beta. It is having a radius R2. And the charge on this one is Q2. The potential on this one is V2. What is C1? C1 is equal to Q1 by V1, which is equal to 4 pi epsilon into R1. C2 is equal to Q2 by V2, 4 pi epsilon R2. Clear? Potential beta. What is the potential here? V1. V1 is equal to Q1 by 4 pi epsilon R1. Here, what is the potential beta? V2 is equal to Q2 divided by 4 pi epsilon R2. What it is mentioned in the question? It is mentioned that the potentials are same. They are raised to the same potential. If that is the case, what happens to the Q1 by Q2? That implies Q1 by Q2 is equal to R1 by R2 beta, which is equal to how much? They are raised to the ratio of charges induced on the spheres raised to the same potential is 6. He is asking surface area. Area of the first sphere. Surface area of the first sphere divided by area of the second sphere, which is equal to 4 pi R square beta. Surface area of the first one divided by surface area of the second one is R2 square, which is R1 by R2 square beta. So, which is 6 square, which is equal to 36 is the answer. Option C is the answer. Like this, little bit conceptual and substitution kind of questions are expected. Now, let us have one more question on the inductance. This was a previous ES question asked in the EC paper. Okay, whatever it may be. Calculate the inductance of a toroid formed by surfaces rho is equal to 3 centimeters, comma, rho is equal to 5 centimeters, comma, Z is equal to 1.5 centimeter. Wrapped with 500 turns of wire. The core has a magnetic material with mu r is equal to 6. Direct substitution kind of question beta. Okay. Calculate the inductance of the toroid formed by the surfaces. So here it is a A, here it is a B, here it is a length wrapped with 500 turns of wire with the core has a magnetic material mu r is equal to 6 beta. So what is the inductance formula speak out of the toroid? Direct formula based question. Mu is equal to n square into L by 2 pi into natural log of B by A. So here mu is equal to mu naught into mu r beta. Mu naught into mu r into n square into L divided by 2 pi into natural log of B by A. So here it is mu naught is 4 pi into 10 to the power of minus 7 into mu r. Mu r value is 6 into 500 square into length, thickness 1.5 into 10 to the power of minus 2 divided by 2 pi into natural log of B by A. It is 5 into 10 to the power of minus 2 divided by 3 into 10 to the power of minus 2. So how much is that inductance? Check out this value. It is 2.3 into 10 to the power of minus 3 Henry or 2.3 millihenry. Clear, beta? Fine. So this is all about the topic number 3, beta, magnetostatics. Now let us start the topic number 4. Time varying fields and Maxwell's equations. I'm going to turn the page here. Topic number 4, beta. Last topic. Time varying fields and Maxwell's equations. So here what we're going to see, Faraday's law, continuity equation, Maxwell's equations, boundary conditions. 4 topics we're going to discuss. Clear, beta? Yes. Fine. Day after tomorrow will be the last session. Today, tomorrow, day after tomorrow. Okay, fine. Let us start with what is called a Faraday's law, beta, here. Faraday's law, or it is also called Faraday's laws of electromagnetic induction. You have been learning this one from your childhood, but let me give some technical definition here. Formal definition here. How it is defined? The EMF induced in the loop is equal to rate of change of magnetic flux enclosed by that loop. The EMF induced in the loop is equal to rate of change of magnetic flux enclosed by that loop and direction of EMF is such that magnetic field due to current which is because of EMF opposes original magnetic field. There are two parts in this statement beta. The EMF induced in the loop is equal to rate of change of magnetic flux enclosed by that loop. This is the first part of the statement. What is the second part of the statement? Direction of EMF is such that magnetic field due to current which is because of EMF opposes original magnetic field. That is the second part of the statement beta. The first part of the statement talks about the magnitude of the EMF induced. Second part of the statement talks about the second part of the statement talks about the direction beta, right? Why? दबा थोड़ा खींचो इसको. Yes. That is EMF induced in the loop beta. What is EMF induced in the loop is equal to minus d by dt of psi m. You have been learning this one from your childhood, isn't it? V is equal to minus d by dt of psi m. Okay. See here, it is a very simple thing. This law starts in your 9th standard or 8th standard physics textbook, isn't it? But here we are interested in defining the integral form and differential form. You would have, this law will start with something like this experimental setup. There is a circuit here and connected to the bulb here. And there is a permanent magnet here. There is a permanent magnet here. Okay. So permanent magnet is surrounded by the magnetic flux lines. Here it is a north pole. Let us say here it is a south pole. If I bring this permanent magnet into the loop, outside the loop, into the loop, outside the loop, what happens, beta? If I bring this permanent magnet into the loop, outside the loop, into the loop, outside the loop, what happens? These flux lines associated with the permanent magnet will going to cut the conductors. So when the flux lines cuts the conductor, EMF is induced in that. Because of that, current flow happens. And because of that, the light will glow. Suppose if I do it with a very faster rate, you'll find very brighter light. If you do it with a very small rate, you'll get very dim light. And if you put it a permanent magnet into that one, and if you're not moving at all, then there won't be any EMF induced. Yes. So you would have gone through this experiment. You would have seen this experimental setup in your high school physics. Just to recall that concept, I have redrawn this one here. But we're going to take something different figure, not that figure beta. Experimental setup, what I mean to say is you would have not done that experiment, just you would have studied that about that experiment. Even in my school also, I have not done any experiments. Vishnu, Ajit. Okay, fine. Let me turn the page here. See here, let us take some diagram like this, beta. Here is a loop. Here is a loop, beta. And this loop is having the flux lines, beta. What these are? Magnetic flux lines. How do you get these flux lines? From a permanent magnet or from the other current carrying conductor. Okay, the source can be anything. These are flux lines, beta. These are magnetic flux lines or original field lines also you can call. What these are? Magnetic or original magnetic field. Okay, so when this flux line, this is a loop, flux lines are like this. So when the flux lines are cutting this loop, what happens? EMF is induced in that loop. What is the reason behind the EMF, beta? Actually, the voltage, electric field is induced. Line integral of electric field is nothing but a voltage, isn't it? So if you talk in terms of the electromagnetic theory, what actually is the electric field? So let me show that one symbolically like this. Here it is E, units are volt per meter. Now what I will do, let us consider the loop direction in this way. Here it is the loop direction is dl. Now let us consider the small piece of area here. Here it is the area is dA, beta. If I put my fingers in the direction of loop, my thumb will going to show the direction of normal. So here it is a normal direction, beta. So the flux crossing through this very small piece of area is a flux density, beta. It is represented by the B. Units are Weber per meter square. Clear? Yes. Now observe carefully. What is this voltage, beta? V is equal to minus d by dt of psi m. EMF in the loop. So what is this one? EMF in the loop is nothing but closed line integral of EDL, which is equal to minus d by dt of surface integral of B dot dA. So this is a vector way of representation. There are two actions are involved here. One is a transformer action, other one is the generator action or motor action you can call. How can you induce the EMF here, beta? Ultimately, what is required here? These flux lines should cut the conductor. One thing is you can fix the loop, you can change the magnetic field lines. Other one is fix the magnetic field lines, change the loop. Yes, so either ways you can get the EMF. Clear? But before going into that discussion, let me focus on this minus sign. Why this minus sign is there? It is popularly stated in your electrical engineering by the word what is called Lenz law. And what is the popular statement for your Lenz law is, it is said that effect opposes its own cause, isn't it? Then why that one? See here, why that is the second part of the question. Second part of the first part of the statement, read out. The EMF induced in the loop is equal to rate of change of magnetic flux enclosed by that loop. And what is the second part of the statement, beta? Direction of EMF is such that magnetic field due to current, which is because of EMF, opposes original magnetic field. What does that mean? Yes, see here, for argument purpose, we have considered that these are the magnetic flux lines. These magnetic flux lines are cutting this loop. So when the magnetic flux lines are cutting that loop, EMF is induced. Yes, so the EMF is induced in this loop. If the EMF is induced in this loop, because of that EMF, the current flow happens. Okay. So as the current flow is happening, there will be a new magnetic field. So the newly induced magnetic field will going to oppose this original magnetic field. That is what the Lenz law is. So the newly induced magnetic field, I will repeat again, when the flux lines are cutting this loop, EMF is induced. Because of that EMF, current flow happens. Because of that current flow, there will be a new magnetic field. So that new magnetic field will going to oppose the original magnetic field. Why it is happening like that? Suppose, for example, that is what the second part of the statement is talking, and that is why the minus sign is there. Let us, just for the argument purpose, just for the argument's sake, you consider that newly induced magnetic field is aiding with the original magnetic field. Just for the argument purpose, consider that newly induced magnetic field is aiding with the original magnetic field. So what happens if it is aiding with the original magnetic field? Effective magnetic field strength increases. Again, the magnetic field lines cutting the loop increases. EMF increases. Current flow increases. New magnetic field increases. Effective magnetic field increases. So the entire system will fall into the regenerative feedback, or you can also call positive feedback. And there won't be any end for that one. If that is true, just by having a copper wire and a permanent magnet, you can generate the power in terms of kilowatts and megawatts, which is absolutely wrong, isn't it? So you are not generating any power here, beta. What is happening is there is a transformation. Magnetic field is converted into electric field here, actually. Okay. So why this minus sign is, if you talk with respect to the physics, it is a stabilizing factor. It is talking about conservation of energy. Okay, fine. You talk about all these things in your electrical engineering in a much detailed manner. Fine. Okay, beta. So in how many possible ways you can induce the EMF? In how many possible ways you can induce the EMF, beta? One is you can fix the loop area, beta. You can fix the loop area constant. But magnetic field is changing with respect to time. Time varying magnetic field. This is called, in the electrical engineering terminology, transformer action, beta. Transformer action. Isn't it? In the case of transformer, You know better than me. Nothing is moving in the case of transformer, isn't it? Just they are excited with the time varying supply. Transformer action. The other way, beta. In how many other way, how you can induce here? Magnetic field constant, beta. Constant magnetic field, but loop area changing. This is called generator action or motor action. Both may happen. Generator action means what? If you have a single turn generator, something like this. There are factor lines here like this. Yes or not, beta? If it is like this, no flux is enclosed. If it is like this, area is increasing, peak. If it is like this, decreasing, zero. So the area is changing, isn't it? So as far as our electromagnetic theory is concerned, we are interested only in this case. This generator action or motor action or rotation action, these are the different names given. For the rotation action or motor action or generator action, you learn about that one in your electrical engineering. But let me touch that one also here. But our interest is more only in the time varying fields here, under the context of electromagnetic theory. Let me turn the page here, beta. See here, for time varying fields, beta, time varying fields, what you can do? You can do some modification to this equation. Here the area is not changing, beta. Only magnetic fields are changing with respect to time. So first I'll write, later I'll explain. I'll translate this general differentiation into partial differentiation. So for the time varying fields, how that equation can be modified? Here it is. Closed line integral of EDL is equal to minus surface integral of dou B by dou T into dA beta. What I have done here for the time varying fields, I have made the general differentiation to partial differentiation. What is the meaning of partial differentiation, beta? When you are differentiating with respect to one variable, other variables are treated as a constant. For example, B of x comma y comma z comma time. Here it is fixed, beta. These are fixed. It is changing only with respect to time. So how can you convey that one mathematically? By using what is called a partial differentiation. Okay, when you're differentiating with respect to time, x, y, z are treated as constants. That means space is constant. Matlab means area is constant. Clear? Yes. So as you notice the integrals on both sides, this is called Faraday's law in integral form beta. This is called Faraday's law in integral form. From the Stokes theorem, what you can do? From Stokes theorem. Stokes theorem. From Stokes theorem. This closed line integral of EDL is equal to surface integral of del cross E dot dA, which is equal to minus surface integral of dou B by dou T into dA beta. Equate these two things. If I equate these two things, del cross E is equal to minus dou B by dou T. This is called Faraday's law in differential form or point form beta. What it is? Faraday's law in differential or point form. So this is what required for your exam. So we have defined the definition form. We have seen the definition form beta. So you need to choose appropriately while you are solving the numerical. This is an integral form. This one is a differential form. You need to choose the appropriate one while you are solving the questions. Now let us talk something about little bit about this generator action also, where the loop is rotating, magnetic field is constant, which is helpful for your electrical engineering. It is called a generator action or rotation action or motor action. Yes, what is the generator action beta? Just it is out of our interest beta. You will learn about all these things in your electrical engineering. Just I wanted to show from where you got all those things. Okay, now let us consider here magnetic force. What is the magnetic force? Magnetic force is equal to Q into V cross B. When you rotate the loop, there are some charges inside that. They are moving, isn't it? When you are rotating the loop in the presence of magnetic field, there are some charges inside the loop. Free electrons are there. They'll experience the force. What is that force? Is magnetic force. Okay. Now what I'll do beta here, this is for the generator action I'm talking. The simple example is a singleton loop is rotating here. Singleton generator. Okay. Okay. Fine here. Now what I'll do, observe here carefully beta. I'll bring the charge here beta. Here it is V cross B. Magnetic force per unit charge. Just forget about this one for the time being. What is the force per unit charge? What you have learned in your electrostatics? Force per unit charge is nothing but an electric field. Array. Isn't it? Observe here. So this is electric field. which is equal to V cross B. Remember, this electric field is not due to charge, but it is due to the velocity of some loop, velocity with which it is moving, rotating, angular velocity or velocity, whatever it may be, in the presence of magnetic field. Array, it is not your electrostatic field beta. It is the motional electric field. What this is called? Motional electric field. This is called motional electric field. So when you have the electric field, obviously it will you will have a potential. Yes. So how do you find out its potential? That is called motional voltage. How do you find out its voltage beta? Vm is equal to closed line integral of Em into dl beta, which is equal to closed line integral of V cross B dot dl. Array, this is called motional voltage. What it is? Motional voltage beta. Yes. So from here you got that VBL sin theta. In the electrical engineering, you will do some approximations. In electrical engineering, you will use the approximated version of that one, or scalar version, I can say. The voltage V is equal to, it is VB. This line integral will going to represent with the L, and the cross product I will going to represent with the sin theta. So this very famous VBL sin theta formula has come from there. So this is more precise vector way of representation. But what is used in your generators is VBL sin theta has come from here. Okay. Units are volts. Clear beta? Yes. Just to create some interest here. Yes, dynamic voltage, you can say. Both is also possible, but you may not be having the applications. The loop is rotating, flux is changing. Just only for the theory. Okay. Okay. So what you need to remember as far as electromagnetic theory is concerned, this one. This is a definition form beta. Okay. And then this is a integral form. This one is a differential form, or you can also call point form. Clear? Let us try to have a varieties of questions on these formulas. Clear? Yes, beta. I'm going to turn the page here. We'll take questions. In a 100-ton coil, if the flux through each turn is T cube minus 2T milliwebers, the magnitude of the induced EMF in the coil at a time of 4 seconds is very simple and straightforward beta. Oh, beta, come on, speak out. How much is the answer? $4.6 beta. $100-ton coil, if the flux through the each ton is T cube minus 2T milliweber, the magnitude of the induced EMF in the coil at time T is equal to 4 seconds is. So what is the voltage here? Minus d by dt of psi m beta. So psi m is nothing but a total flux here. So how many number of turns here? 100 into flux through the each turn is T cube minus 2T into 10 to the power of minus 3. Here it is 10 to the power of minus 1. Differentiation of this one is 3T square minus 2. Substitute at that point at time T is equal to 4 seconds. So here it is minus 10 to the power of minus 1 into 3 into 4 square minus 2, which is minus 4.6. So here just we need a magnitude beta. 4.6 volts is the answer. Let us have one more question beta. Is asking magnitude beta. Magnitude. That is the reason why we have taken only the positive value. Let me turn this one. Let us have one more question. Here is a question. I'll just read out. I'll write down. A square loop of 4-meter side is placed in XY plane with its center at the origin and sides along the coordinate axis. If the magnetic flux B is equal to 0.2 x cap minus 0.3 y cap plus 0.4 z cap into e to the power of minus 0.1 into t Weber per meter square. Find voltage induced in the loop at time t is equal to 10 seconds. हाँ बेटा. A square loop of 4-meter side is placed in the XY plane with its center at the origin and sides along the coordinate axis. If the magnetic flux density B is given beta, find the voltage induced in the loop at time t is equal to 10 seconds. Clear? Observe here beta carefully. Let me draw some rough diagram here. So the loop is placed in the XY plane. That means Z is equal to 0. Yes. Here it is X. Here it is Y. Here it is Z. Here it is negative X beta. Here it is negative Y. So the loop is placed in the XY plane. Okay. Suppose if I consider the small piece of area here. What happens to the area dA? dx into dy into z cap beta. Because this is in the XY plane. And what is the side of this one? It is 4-meter side. And in this region, there is a magnetic field beta B. Here the vector form is given. If the vector form is given, he is asking for the potential. What you have to use? You cannot use this one. This is the definition form. When the flux is given, you can use this one. When the flux density is given, you have to use this one, this form. Integral form. Clear? So everything is vector here. So EMF induced in the loop. Voltage V is equal to closed line integral of EDL, which is equal to minus surface integral of dou by dou t into dA beta. So as the flux density is given, that means, so this is a thing need to be used. Minus surface integral of dou by dou t of B. What is B? 0.2 x cap minus 0.3 y cap. Space would not be sufficient. I'll go to turn the page. Minus surface integral of dou by dou t of point 2 x cap minus 0.3 y cap plus 0.4 z cap into e to the power of minus 0.1 into t into differential area is dx into dy into z cap. Clear beta? Just bring this differentiation outside. Dou by dou t of e to the power of minus 0.1 into t surface integral of 0.2 x cap minus 0.3 y cap plus 0.4 z cap. Dot product with dx dy z cap. So here this dot product remains and everything will go 0. So here it is minus 0.1 into e to the power of minus 0.1 into t, 0.4 into dx into dy. Bring this one inside beta. 0.4, 0.1 into 0.4 into e to the power of minus 0.1 into t. Here it is dx into dy. What this is indicating? This is indicating the area of the loop or loop area. Yes, let me proceed further here. So what is the area of the loop? 0.1 into 0.4 into 4 into 4 into e to the power of minus 0.1 into t. So here it is 0.64 into e to the power of minus 0.1 into t beta. He is asking at what point? At time t is equal to 10 seconds he is asking. Just substitute there. 0.64 into e to the power of minus 1, which is 0.64 by e beta. How much is that? Check out this value. 0.23 volts. 0.23 volts is the answer. Is that correct? Please cross check. Let me turn the page here, beta. Let us have one more question. Is that correct? 0.23? 0.235, yes. Why? One of your friend is asking why not minus z cap here not taken. In general, we'll take plus value only. That is only the by convention. Unless and until it is mentioned. That I've given in the that I've explained in the very first lecture. Okay, let us have one more question, beta. Select the value of k so that the following fields E is equal to kx minus 100t y cap volt per meter and h is equal to x plus 20t z cap ampere per meter satisfies Faraday's law in medium mu is equal to 0.25 Henry per meter. Yes, beta. So you need to use the differential form of this Faraday's law. It is already said these are satisfying the Faraday's law. The question is select the value of K. That means you need to find out the K value. E and H are given. It is also said that it is satisfying the Faraday's law in the medium. Mu is equal to 0.25 Henry per meter. So what is the Faraday's law, beta? Del cross E is equal to minus dou B by dou T, which is equal to minus dou by dou T of mu into H. The mu value is 0.25, right? So here it is. Curl of E is equal to minus dou by dou T of 0.25 into H beta. So curl of E is equal to minus 0.25 dou H by dou T. Now expand this one beta. Bas khatam. Here it is x cap, here it is y cap. So dou by dou x, here it is 0. Which component of electric field is given? Y component. So here it is y cap. Here it is dou by dou y. Here it is kx minus 100t. Here it is z cap. Dou by dou z. Here it is 0. Minus 0.25 dou by dou t into x plus 20t into z cap. Here you are noticing the z component beta. So what I'll do, I'll just equate the z components on both sides without wasting time. What is the z component on the left side? Z cap into this minus this into this, which is dou by dou x of kx minus 100t, which is equal to minus 0.25 dou by dou t of x plus 20t. Here it is k is equal to minus 0.25 into 20. So k is equal to minus 5 is the answer. Okay, beta. Let us have one more question on the Faraday's law. I'm going to turn the page. Now you can easily answer this question. This was one of your previous questions. Consider a one-turn rectangular loop. One-turn rectangular loop of wire placed in time varying magnetic field B of t is equal to 0.25 sin omega t Weber per meter square, where omega is equal to 2 pi into 50 radian per second, as shown in figure. The resistance of the loop is resistance of the loop is 0.4 ohms. The power absorbed by the loop from the magnetic field is here is a magnetic field like this given, diagram given. So how much is this beta here to here? 10 centimeter. Here to here it is 5 centimeter. Okay. So what you need to find out here? You need to find out the EMF. Okay. Fine. Now, here this is a scalar quantity is given. Let me highlight it. It is a singleton loop. Flux density is given, but it is a scalar quantity. You can just multiply with this area so that you will get the flux, magnetic flux. After that, you will get the voltage, and the resistance of the loop is given. He is asking power absorbed by the loop from the magnetic field. That means he is asking the average power. Obviously, power calculations means you have to do the average power. So fine. So do this one. Let me turn the page here. First, what you need to do. What is the voltage beta? V is equal to minus d by dt of psi m, which is equal to minus d by dt of B into area. Why? Because it is a constant. Constant in the sense it is not changing with respect to vectors. Yes. So just multiply with the area here. So which is equal to minus d by dt of, what is this one? Here it is area. What is the area of the loop? 10 by 5 centimeters. So here it is 5 into 10 to the power of minus 4 into 0.25 into sine 2 pi into 50 into t. That's the thing. Just to differentiate this one. Here it is minus 50 into 0.25 into 10 to the power of minus 4 into 2 pi into 50 into cos 2 pi into 50 into T. So how much is this entire value, beta? Please help me. How much is that entire value? Point 3926. Please cross check. Mr. Swain. 3926. 0.39 minus 0.3926 cos 2 pi into 50 into T. So what is the peak value? Vm is equal to 0.3926 beta. He's asking a power observed. Power in the sense average power only. So what is the average power? P average is equal to Vrms into R, isn't it? Vrms square by R beta. Vrms square divided by R. That's all it is. So how much is this? What is the RMS value beta? Vm by root 2, isn't it? Vm square by 2 into R. So here it is 0.3926 whole square divided by 2 into R. What is R? 0.4. So what is P average? Point 1926, approximately 0.2 beta, 0.2 watts. Okay, your class will be up to 8 p.m. only. So that is the reason why we'll take very short break now. After break, this is all about the Faraday's law. We'll take what is called a continuity equation followed by the Maxwell's equations. We'll see how much we can do in the today's session for the Maxwell's equations. And the exact interpretation, understanding of the Maxwell, we'll derive the Maxwell's equations in the today's session. And the interpretation and all that story we'll postpone to the next session. Okay, let us have very short break, not more than 15 minutes. Okay, welcome back, beta. Now let us discuss what is called a continuity equation. I'm going to put the foundation for the Maxwell's equations. We'll see how much we can do in the today's session. We are left with the 1 hour more. Continuity equation. Continuity equation talks about conservation of charge. What is this continuity equation? Let me write down the statement here first. The net current coming out of any closed surface is equal to rate of change of charge decrease inside that closed surface. The net current coming out of any closed surface is equal to rate of change of charge decrease inside that closed surface. That is I net is equal to minus d by dt of charge inside. See here, before going into that, let me have some analogy here. Let us consider the charges better. This is a closed surface, this bottle. Inside this bottle, there is a water. If I make a hole to this one, what happens? Water will come out. Suppose, let us say, for the argument purpose, 1 milliliter is coming outside per every second. What will happen inside this one? 1 milliliter will going to decrease inside this bottle for every second. If the 1 milliliter is coming outside, what happens, beta? 1 milliliter will going to decrease inside this one. It's or not? Simple logic. Okay. Remember, that is only true when the amount of water is fixed. If the water is coming from here and if you are pouring the water from the mouth, that will not be the truth. If 1 milliliter is coming outside, 1 milliliter will going to decrease inside this. I'll apply the same logic to the charges. Same analogy to the charges. Let us consider the closed surface, beta. This closed surface is having some 1000 lines, 1000 charges. This closed surface is having some 1000 charges. If 10 charges are coming outside the closed surface per every second, if 10 charges are coming outside the closed surface per every second, what will happen? Obviously, 10 charges will going to decrease inside the closed surface per every second. So the 10 charges coming outside the closed surface per every second is nothing but a net flow of a current. Why? Because it is coming. Charges are coming out from the closed surface. So here it is a net flow. So read the statement here. The net current coming out of any closed surface is equal to rate of change of charge decrease inside that closed surface. That is I net is equal to minus d by dt of charge which is inside. Now let us consider some closed surface here, beta. This is a closed surface. I am putting the dots to create the feel that it is a three-dimensional one. I'm putting to this, I'm drawing this shape last time. And here inside there are charges beta. How it is characterized like a volume charge. Rho v coulomb per meter cube. Now inside this one, there is a volume beta. The volume is dV. On this one, there is an area. Okay. Here is the area. What is the area is dA. What is the normal direction is outwards beta. So the current coming out of from this very small piece of area is current density. What is the current density is a J. Units are ampere per meter square beta. Remember here, no replacing. No replacing mechanism of charges. So the number of charges are fixed. So the rate which are coming outside, the same amount of rate will going to decrease. That is what this continuity equation is. So can you write this one in the vector form? Current in terms of current density. Here it is surface integral of J dot dA, which is equal to minus d by dt of charge. What is the charge beta inside? It is a volume charge. Rho v into dV. And here it is a net current. Net current in the sense you have to consider closed surface. Clear? But here we are interested only in the time varying case, isn't it? So this partial differentiation can be, general differentiation can be turned into the partial differentiation. Let me turn the page here. For time varying case, what happens? For time varying case, this general differentiation can be closed surface integral of J dot dA is equal to minus volume integral of dou rho v by dou t into dV. For example, why like that beta? This rho v is function of x comma y comma z comma time beta. Okay. So here the space is fixed. X comma, these are fixed. Okay. Here it is changing only with respect to time. Varying only with respect to time. So as you have noticed the integrals on both sides, this is called continuity equation in integral form beta. Continuity equation in integral form. Now further what you can do from the divergence theorem. From the divergence theorem, This closed surface integral of JDA can be written as volume integral of divergence of J into dV. Clear? Yes. So here this is also equal to minus volume integral of dou rho V by dou T into dV. Just equate these two things better. So you're going to get divergence of J is equal to minus dou rho V by dou T. This is called continuity equation in differential form beta. Continuity equation in differential or point form. Okay, fine. So these are the, keep this one aside beta. We're going to use this one later. Now let me turn the page here. Keep that continuity equation aside. Let us focus on the equations what we have developed so far. Now let me write down the equations what we have developed so far. We have seen that del cross H is equal to, consider del cross H is equal to J beta. The other one is del cross E is equal to minus dou B by dou T. Next one, divergence of D is equal to rho V. Next one, divergence of B is equal to 0. These are the different laws which was proposed by the various scientists. This is Ampere's law. This is Faraday's law. This is a Gauss law for electric field, Gauss law for magnetic field. Okay. But when the Maxwell observed these equations in the second half of the 18th century, around in the year 1867, so he had a problem with the first equation. Before Maxwell, people used to think that what is the interpretation of this equation? To put it in a simple words, what we can say that the magnetic field is due to the conduction current. That is what the people used to think and people used to believe. But what Maxwell has said, no. Magnetic field is not only due to the conduction current, but also due to, there is a one more term here. Later we will going to get that as a displacement current. And people was not ready to accept what is this Maxwell theory. And after around some 15 years later, after the Maxwell, the Hertz has experimentally proved the existence of displacement current. Yes. Okay. So what we'll do first, let me do the purely mathematically. Later we'll going to have some interpretation. Clear? So we'll understand what is the problem with this del cross H is equal to J mathematically, then how it was rectified, and later you're going to get what is called a nicely Maxwell's equations. Fine. Let us try to understand what is called inconsistency, or it is all you can also call error in the Ampere's law. Inconsistency. Inconsistency in Ampere's law. or error in the Ampere's law. Now consider beta. Del cross H is equal to J beta. Apply the divergence on both sides. What is this divergence of a curl of a vector beta? 0. So which is 0 is equal to divergence of J beta. That means divergence of J is equal to 0. But from continuity equation, what is divergence of J beta? Divergence of J is equal to minus dou rho V by dou T. So this curl of H is equal to J is not satisfying the fundamental law of conservation of charge. So this is a inconsistency, or you can also say error. Inconsistency, or you can also call it as a error beta. So now let us try to correct that one. Let me turn the page here. So that is called a generalized Ampere's law. What it is beta? Generalized Ampere's law. Let del cross H is equal to J plus P beta. What is that P? P is an error correction vector. Yes, or simply correction vector. So from the previous analysis, we have noticed that there is something problem with this curl of H. So let us try to correct that one. Correction vector. Okay. Now what I'll do, I'll apply the divergence on both sides for this one. That means divergence of curl of H is equal to divergence of J plus divergence of T. So this is equal to 0 is equal to divergence of J plus divergence of P. So from here, divergence of P is equal to minus of divergence of J. From continuity, equation, what is the divergence of J beta? Is equal to minus dou rho V by dou T. So bring this one here and substitute here. So the divergence of P is equal to dou rho V by dou T beta. From Gauss law, what is rho V beta? Rho V is equal to divergence of D beta. Substitute this one here. So what happens to the divergence of P? Is equal to dou by dou T of divergence of D. So divergence of P is equal to divergence of dou D by dou T. Clear? On comparison, what you will going to get P value? P is equal to dou D by dou T. You have got a correction vector beta, isn't it? Now let us check its units. What are the units for this one? Here it is dou by dou T. Dou by dou T is nothing but per second. What is this D beta? D is nothing but a coulomb per meter square. What is this coulomb per second is nothing but ampere. So here it is. Are ampere per meter square, it is a current density. Are what kind of current is this? This current is not due to the flow of charges beta. This is due to the time varying electric field. Something strange, something new. Are aisa kaisa ho sakta? Can the time varying electric field give the current? Yes, that is what the Maxwell has proposed. And he has named this as a displacement current. And it is integrated with the JD beta. JD is equal to dou D by dou T. Ampere per meter square. What is this one? This is displacement. Current density. Displacement current density. Are time varying electric field is also giving current. The people were not ready at that time when the Maxwell proposed this one. Of course, I have explained in a simple 3 to 4 steps. He has shown the proper mathematical. He has proposed this theory in 2 volumes. A treatise on electricity and magnetism by James Clerk Maxwell, volume number 1, volume number 2. Yes. So let me turn the page here. Finally, after correction, what happens to this del cross H beta? Del cross H is equal to J plus dou D by dou T. This is called generalized Ampere's law in differential form or point form. This is generalized Ampere's law in a differential form. Now what I'll do, I'll apply curl on both sides beta. Surface on both, surface integral on both sides. Surface integral of del cross H dot dA, which is equal to surface integral of J plus dou D by dou T into dA. What is this curl under the surface integral is nothing but a closed line integral. Closed line integral of H dot dl is equal to surface integral of J plus dou D by dou T into dA. This is called generalized Ampere's law in integral form. Clear beta? Fine. Let me turn the page here. Let me summarize what are the Maxwell's equations are. So finally, we have got what is called Maxwell's equations. Yes, there are two forms of Maxwell's equations. One is a differential form, other one is an integral form. One is differential form. The other one is integral form beta. There was no numbering given by the Maxwell, but we'll follow this numbering. What is the first Maxwell equation? Del cross H is equal to J plus dou D by dou T. Number 2, del cross E is equal to minus dou B by dou T. Number 3, divergence of D is equal to rho V. Number 4, divergence of B is equal to 0. What about this one beta, integral form? Closed line integral of HDL is equal to surface integral of J plus dou D by dou T into dA. Next, number 2, closed line integral of EDL is equal to minus surface integral of dou V by dou T into dA. Third one, closed surface integral of dDA volume integral of rho V into dV. Fourth one, closed surface integral of B dot dA is equal to 0. There is one more equation which is not a Maxwell equation, but let me write down here, which is continuity equation beta. What is that continuity equation? Is divergence of J is equal to minus dou rho V by dou T. The other one here is closed surface integral of J dot dA is equal to minus volume integral of dou rho V by dou T into dV. This is a continuity equation. If you see these equations individually, this is a Ampere's law, this is a Faraday's law, this is a Gauss law for electric field, Gauss law for magnetic field. What was the contribution of the Maxwell beta? The contribution of the Maxwell is this one. He has just introduced the concept of displacement current. And he has named all the four equations as a Maxwell's equations. Is it not cheating? It's not cheating beta actually. He has unified the electricity and magnetism. Before Maxwell, people used to treat the electricity and magnetism as a distinct phenomena, separate phenomena. They used to think that electrostatics is separate branch of physics and magnetostatics as a separate branch of physics. But what Maxwell has said, he said that there is nothing like electrostatics and magnetostatics. And he also said that there exists only one phenomena. What is that phenomena? EM phenomena. And electrostatics and magnetostatics are special cases of that. Okay, fine. And one more thing here. Time varying magnetic field is giving electric field. Time varying electric field also should give magnetic field. Isn't it? Then this is called EM phenomena. Suppose for example, if this term is not there, time varying magnetic field will give electric field, but there won't be any vice versa mechanism. But nowadays, in this modern world of electrical engineering and electronics, you cannot deny the fact that there is a EM phenomena. In the second half of the 18th century, people was not ready to accept the concept of EM phenomena and displacement current. At that time, okay. And around some 15 years later, after the Maxwell, the Hertz has experimentally proved the existence of displacement current and EM phenomena. But nowadays, there is no question, isn't it? We are living in the region, in the field of EM phenomena. EM fields are around us, your long length transmission lines, fiber optic cable, satellite communication, whatnot. Yes, see here, time varying magnetic field is giving electric field. Time varying electric field also should give magnetic field. Then this is called EM phenomena. Clear? Suppose if this term would have not proposed by the Maxwell, can you understand the existing phenomena? No. So that is the reason why this Maxwell theory is very important. The displacement current is very important. We're going to have the physical interpretation of that one, these things later. Okay. Let me turn the page here. Before turning the page, let us have some interpretation here. In a simple words, how you can interpret these equations is, the first equation is saying that the magnetic field is due to two types of currents. One is due to the conduction current, other one is due to the displacement current. What is the displacement current, beta? Is time varying electric field. So the space varying magnetic field is due to the time varying electric field and also due to the flow of charges. Next one. The space varying electric field is due to the time varying magnetic field. Third one. The source for the electric field is a charge. The source for the magnetic field is also charge. But what kind of charge is that? Dipole charge, beta. So what these two equations, third one and fourth one, are talking about? These are talking about the source equations. What these two equations are? These are source equations, beta. And what these first two equations are called? First two equations are called effect equations. Why? Because magnetic field is related to electric field. Electric field is related to magnetic field. Electric field is related to magnetic field and vice versa. So these are called effect equations. And there is some special name given for this equation. What is that special name? This is only the equation where you do not find any source. Here is a source, here is a source, here is a source. So this is the equation which purely relates the effects. Okay. So this equation is, the other name for this one is intrinsic relation. And what is this continuity equation, beta? Because of this continuity equation, you are having this displacement current. Because of this displacement current, there will be what is called a EM phenomena. I'll repeat again. If you go back to the math derivation, If I go back to the derivation, I've said that this was not satisfying the continuity equation. That is the reason why after making the correction, you have got this term. So this term is demanded by this one. So this one will give this one, and this one will give this one, and this one will give this one, is nothing but a EM phenomena. So the EM phenomena is existing because of this one actually. So that continuity equation is called necessary condition for EM phenomena to exist. What it is? Necessary condition for EM phenomena to exist. Clear, beta? And one more thing, these are the Maxwell's equations. I need to talk more about this EM phenomena inside the perfect conductor, and how the current flow happens inside the capacitor, and what is the circuit theory. This is a scientists have introduced this. Maxwell has introduced this Maxwell theory. But to make this is how you need to understand your electrical engineering with the help of these equations. They are looking very terrific, isn't it? So when the engineers observed these things, they have simplified them. They have approximated them. Then the approximated version, simplified version of this EM theory has led to what is called a circuit theory. So the circuit theory has become very popular. But whenever the circuit theory fails, you need to look back to this EM theory, isn't it? So this is where the circuit theory was developed. So scientists has given this Maxwell theory. So the engineers have simplified that one. Okay, fine. So that also we need to do. But I want to make one more note here. Suppose if you want to get the things for electrostatics and magnetostatics, what you need to do? This one, dou by dou t, you have to make 0. That's all it is. Clear? So how these can be modified for the static case, beta? I'll going to turn the page. For static fields, what happens? For static fields, dou by dou t is equal to 0, beta. There are two things here, differential form and integral form. The other one is integral form. So how the first equation will be modified, beta? Del cross H is equal to J. Second equation, del cross E is equal to 0. Third equation, divergence of D is anyhow is equal to rho V. Fourth equation, divergence of B is equal to 0. This one, beta, first one, closed line integral of HDL is equal to surface integral of J dot dA. Second one, closed line integral of EDL is equal to 0. Third one, closed surface integral of DDA, same thing, is equal to volume integral of rho V into dV. Fourth one, closed surface integral of B dot dA is equal to 0. Here, divergence of J is equal to 0. Here, closed surface integral of JDA is equal to 0. Yes. So this is electrostatics. This is magnetostatics beta. This is magnetostatics. This is magnetostatics. This is magnetostatics. This is magnetostatics. This is electrostatics. This is electrostatics. This is electrostatics. This is electrostatics. Okay. So the electrostatics and magnetostatics are special cases of EM phenomena. So what is so great about these Maxwell's equations? Right from the very first lecture, I was saying what that is called the common thread which runs behind all your in electrical engineering is the EM phenomena. So what we'll do, we need to focus on little bit more on this displacement current. Okay, we're going to take some different, we're going to understand with the help of we're going to take what is called different significance so that you'll really appreciate what these Maxwell's equations are. This mathematical formulation and everything was given by the Maxwell actually. Let me turn the page here. We'll take what is called a significance of displacement current. Significance of displacement current. Significance of displacement current or current density. Number 1 beta, let us try to understand what is called a EM phenomena. That is what I've been saying right from the beginning of the lecture. EM phenomena. What is that EM? Before that, what is this J? J is equal to sigma into E. What is this D? D is equal to epsilon into E. What is this B? B is equal to mu into H. Okay. Let us consider the Maxwell's equations. What is the first Maxwell equation beta? Del cross H is equal to J is equal J plus dou D by dou T. What is the second one? Del cross E is equal to minus dou B by dou T. So what happens to this one? Del cross H is equal to sigma into E plus dou by dou T into epsilon into E. This one, del cross E is equal to minus dou by dou T of mu into H beta. See here, what you have noticed here is time varying electric field is giving space varying magnetic field. Again, magnetic field will give electric field. Again, electric field will give magnetic field. Again, magnetic field will give electric field. Array, this is what the EM phenomena is. Especially this one. This was a major contribution of the Maxwell. This is what we have been calling what is called a EM phenomena. Yes. So the time varying electric field, let me put it like this. Time varying electric field is giving magnetic field. Time varying magnetic field is giving electric field. Electric field is giving magnetic field and so on. Array, this is what the EM phenomena is there, isn't it? Suppose let us say, if this term would have not introduced by the Maxwell, if this term would have not there, is there any EM phenomena? No. If this term is not there, beta, what happens? Only time varying magnetic field will give electric field. But there won't be any vice versa mechanism. Time varying magnetic field is giving electric field. In the same way, time varying electric field should also give magnetic field. So that is given by what is called a displacement current. Remember, EM phenomena is not because of the Maxwell's equations. EM phenomena is not because of the Maxwell theory. EM phenomena is not because of the Maxwell. EM phenomena is already there. If the charge is moving, if the charges are accelerated around the current carrying conductor, there is a EM phenomena. The EM phenomena is there in the nature. Maxwell has proposed some concept of displacement current to understand the already existing phenomena. Is gravitational force is due to Newton? No, beta. Gravitational force is there already in the nature. Newton has proposed some theory to understand the already existing phenomena. Here also same story. So here this is called EM phenomena, beta. Symbolically, we can show like this. Here it is EM phenomena. Symbolically, I'm showing like this. Even though if you consider for the free space, this part will go zero. Because in the free space, there is no conductivity. This part will disappear and still there is a EM phenomena. Yes or not? So the EM phenomena is existing around that. That case is very important for telecommunication engineers. Fine. So I need to talk something more about all these things, but I'll postpone to the next session. Now let me open the session for your doubts. We'll discuss the EM phenomena in the free space. Free space is not required. Anyhow, we are not doing any communication things. We'll discuss inside the perfect conductor. We'll understand what is that skin effect concept in your long length transmission lines. And then we'll take how the current flow happens inside the between the plates of a capacitor. And we'll also see with our own interest how the circuit theory is developed from the EM theory, followed by the numericals, followed by the boundary conditions. Yes, fine. So now the session is open for your doubts. Yes, Mr. Swain.
Hello, sir.
Yes, beta.
Sir, that continuity equation.
Huh?
Continuity equation.
Uh,
Already exist means anyone proposed?
That is just a observation, conservation of charge.
Conservation of charge. Okay. And say that
Basic
flow
laws
of,
of physics. Basic law of physics.
okay, okay. And sir, that means it will be vice versa. That E will be produce H and H will be produced. That you said a term that time varying electric field will produce a space of that
Space varying magnetic field.
that is space. Means again that time varying magnetic field will produce a electric field which is in space.
Yes.
This is correlated.
Ah.
Okay. Sir, another doubt is that we are when we are deriving that del dot t is equals to rho v.
Del dot D.
uh,
Pass law.
Here we are not considering what is the means we are considering all type of distribution means point charge that is surface charge or something all type. But rho v concept means it will be only for volume. Means that we are deriving that if there is a closed surface which is means let's suppose there is a surface charge present inside that will be equivalently converted to that much of volume which will be distributed on that volume. The charges are distributed. Is that mean?
No. There is a closed surface here. It's just you are taking the volume charge. You are considering some space and charge in that.
But sir, derivation says that d dot ds is equals to rho v.
Divergence of D is equal to rho v. Yes.
या फिर closed that is q enclosed.
Charge enclosed. Yes.
Enclosed. Then that charge enclosed is can be any form. That is line form. That will be surface form.
Yes, that again. Yes, you can say light. Yes, okay.
Means,
You can. Your interpretation, yes, correct.
Means I think means it was a doubt previously actually. Means is it means we are there is also question. This is always in a question it is said that find a rho v. What is rho v is only for volume, but there is also existence of a surface charge also. We don't know what type of distribution.
Actually, everything is a volume. If you really talk.
Okay.
Why everything is volume? Why? Because you can have a line. Can you have a line with the zero thickness? No.
No. Yes.
Inside this one, there is a volume.
Volume. Okay.
In the sheet also, there will be a thickness. Inside also, there is a volume.
And sir, that problem we are talking, that is area of the line charge is 5 mm square. That problem we are taken. Here is the practical problem. Means a line charge is actually not exist. Na? Yes.
Relatively, we can treat it as a line charge. So I'm talking strictly.
Sir,
What distance you are? See, if I am holding this marker in my hand. If I'm near to this one, it is looking like a cylinder for me.
Yes, sir.
If I go to the 1 kilometer, it looks like a line.
Okay.
If I go to the 5 kilometer, it looks like a point.
Yes, sir.
After that, it will disappear.
Okay.
So relatively at what distance you are measuring, that is important.
Sir, from this concept onward, yesterday we have done a problem that is a force per unit length. For that, we are taken that ideal. So that is a force density. Ideal, and I said that JDV something.
Yes.
Yes. Sir, you are taken ideal. Means that this is actually the question is mentioned in a volume format. Question is said in it that is something 5 mm square. Means it is already
the
given
force
in
density.
then how you taken, sir, that it will be in line format. Means ideal means that the thickness should be very low, because but here the thickness is given.
Because line current is given, that is the reason I have considered that.
Means line current means if that thickness is tends to 0, then ideal. We can say that this is ideal.
As it is mentioned, the line current some with how much 5 amperes, sir?
5 ampere, yes, sir.
This is only the reason I have considered ideal.
Okay.
Otherwise, I need to take this I by dA,
Okay.
area and all the story.
Yes. Thank you, sir.
Yes, sir. Avinash.
Hello, sir.
Yes, beta.
Sir, you have told the various forms of Faraday's laws, that is integral form and differential form. So, sir, which form we have to use, sir, in numericals?
We have solved the questions on 3 different forms. So 3 different forms are expected questions.
Yes, sir, but how you will identify, sir, that which form we have to use?
Depending on the data what he has given. See,
Huh.
depending on the given data, that's all. What he has given, flux is given. That is the direct reason why directly I have considered the flux.
Yes, sir.
That is the thing. And here, vector form of magnetic field is given. That is the reason why I have considered vector form.
Vector form. Okay, sir.
That's how you need to identify based on the question itself.
All right, sir. Sir, slide number 301.
301.
Sir, here you are told that which one is the magnetostatics and the electrostatics. Will you please explain? Tell once again.
This is magnetostatic, where magnetic field is there. This is magnetostatics.
Okay, sir.
These are electrostatics.
Okay, sir. Thank you, sir.
Any more questions? Okay, then we'll going to close the session. Okay, we'll continue tomorrow. Bye, friends. Take care. Good night.